from computer engineering at UC Santa Cruz and her doctorate from computer science at MIT. She's also very into teaching and teaching project-based collaborative courses, done a lot of development of iOS apps for people with visual impairments and things like that, and is actually quite vocal for other social issues. So without further ado, I'll kick it over to Ari, who's going to do the first symposium at CRV.
Well, thank you so much for inviting me to talk today. I'm going to unfortunately not talk about my work at robust.ai, but you can learn about me and how I think about some problems that are interesting, and maybe you can infer things about it as you will. Today, I'll talk about doing robot manipulation without using perception. It's kind of ironic to be leading the sensor fusion discussion. I do want to point out that this work will get to incorporate state estimation, learning, and planning. We won't be considering observations from vision, and I hope will be interesting to you and you'll learn something. I won't go through all the work I did in my PhD, but I will try to share some of the highlights and reflections I have looking back at it. Before I go too far, I do want to talk about what inspired this work. I was interested in getting robots to be reliable in unstructured household domains. Now, usually we look at robotics and where is manufacturing, like where are robots really good at manipulation? We go to manufacturing. So I don't know if you guys have seen vibratory bowl feeders, but they're pretty fantastic. They are these systems that can just jumble parts around and move them around, and they hit objects, obstacles, and they get reoriented. And somehow they manage to make, order out of chaos. And they don't do it by sensing. They do it by forcing the objects into desired configurations. Like right here, you can see the objects are moving and they get hit by a fixed obstacle to realign them. I honestly am bamboozled because these things happened decades ago, and somehow we still struggle to do manipulation in household and different domains. I think there's huge differences in the types of problems, and I learned a lot more about them during my PhD, but I did want to bring some of these ideas from bowl feeders to my work. So right here, I don't know if you see this like U-shaped diagram. I was looking at tabletop manipulation problems, and I wanted to do Tetris. I think as a PhD student, sometimes you have your thing you want to do. I really want to do Tetris. Now, Tetris is hard because just like the objects were convex, were not convex, and so the pushing them would have very, very interesting sort of effects on their actions. So I ended up looking at approaches to solve these type of arrangement problems where blocks were kind of in these more orderly arrangements. And this work was still kind of hard to do because the Peer 2 had like fat little fingers around it, and it couldn't just like place a block where you want it to be. So you couldn't just do pick and place. You had to place the objects and then move them to where you want to go. And suppose you had a different type of manipulator that could place the object more precisely, you'd still have issues that we see in manufacturing, like things getting stuck and jamming. So in this case, I had to do something a little bit different, or at least I approached it differently by wanting to place objects and then push them around. The other thing is this problem did have challenges for sensing. I think, after the fact, I realized this probably was the hardest sort of situation to use off-the-shelf sensing algorithms with. The colors were very similar. You couldn't really segment the objects. Things were difficult to use black box tools. Here's an example of the robot executing one of the plans that I worked on. Now you'll notice there is an assistant in the video who is providing the block to the robot. That's me. And the robot assumes it knows where the object is, like assumes it can introduce an object, but from there on, it's doing all open loop actions. So my insight from vibratory bowl feeders was be the change you want to see. Let's have robots that introduce objects and move them to where they want them to be instead of just looking at them. Some of the latter half of my PhD work did approach this Tetris domain where I would add fixtures to try to improve an existing plan. But today I'll be focusing on the block world where I would use pushing against a flat aligned obstacle to try to reduce our uncertainty of the problem. This work had to deal with non-deterministic actions. So here, a robot's doing the exact same place and push, and the effect of the actions will be very different. So even though the robot gets to introduce objects, there's substantial noise in the placing action, and there was noise in the pushing action. In terms of where is this work framed at, I was solving what is modeled as a POM-DP, except I was solving it with conformant planning because I wasn't using observations. Now, this is kind of, instead of doing sense act plan, I was just planning and acting. And the output of my planner was a sequence of open loop place and push actions that would move objects to their goal configuration. This work was motivated by wanting robots to be more reliable. I was infuriated when there was this demo sort of approach to robotics, at least that was something I felt at the time, where you'd always have the video running and you'd hope it'd work. I really wanted to create software that made robots work all the time, and sensorless planning is robust by definition. I think there's a practical aspect of this work where, honestly, the robot will move its arms in front of its head and it can no longer see what it's manipulating. And we need to think about that at some point if we want to have robots that have onboard sensing capabilities. In this work, I'm going to leverage that insight from the vibratory bowl feeders of using fixtures to push objects against to reduce uncertainty. And you'll see that idea just drives the entire project. To find open loop plans, I did a graph search in what's called belief space. Now, in a typical graph search, you will have a state and you'll do actions to expand the state, and figuring out how one state evolves into the next state can be hard in this framework. So to solve it, I did a composable structure transition function that I learned from doing pushing of blocks against a wall in a physics simulator. One of the things that's different in this work is that we are planning in belief space, where a belief state represents all possible states of the world. You might be more familiar with state action next state, a common tuple in a learning problem where we try to predict how an action will affect a single state. In this work, I'm doing belief state action next belief state, and I'm trying to model how an action affects a set of states. I'm also doing this in a graph search. So because I'm doing a graph search, there's some implications of what the desired solution will be. We're going to want the solution to be compact so we can represent it as a state within a search. And we're also going to want it to be efficient to expand this state in order to be able to search this graph and grow a tree and find a goal solution. To give you an intuition on what a belief state transition looks like in this domain, I have an example of one of the data points from my data set. So here on the left in the light blue is the initial pose, or samples of initial poses from a belief state, 1,000 of them that we pushed with this paddle into the wall on the right. And then over on the right side, you could see the darker blue is the final pose of these objects. One thing that you might notice is if you change the vertical offset between the objects, you'll have a very large difference in output. So because the paddle was, higher above than the object, things would roll off on the bottom. We collected data for single blocks, 2 blocks, and 3 block pushes because we wanted to try to capture this type of information about when you're pushing sets of objects and how does the effect happen? In order to represent this, we enforce a structure on all pushing actions that we considered. The object has to be constrained on both sides of the wall. Now, this could actually be quite expressive. For example, our model could do a belief state transition for this type of structure because it was composable. We were able to represent this because this bottom row of blocks would not get affected by the pushing action. So when we did the transition, or when we modeled the transition, we just didn't include them in the update function. This also was limiting because we couldn't consider pushes like this, where this lower left-hand block was not going to get affected. So one of the things that happened was, as we're going the tree, sometimes there are states we just didn't expand because we weren't able to enforce the structure on the pushing actions. An aspect of this work that was unique was how we represented an object's belief. We represented it as a configuration and uncertainty, where the configuration was a pose, x, y, theta, and the uncertainty were intervals, delta x, delta y, and delta theta. This allowed us to consider the pose as something that could have a deterministic update during the push, but the uncertainty was something we could learn using our trained model. The way we did this was through two stages. We'd have a forward pass where we would produce what's called a sequential contact path to determine what is the order objects will get hit when pushed into an obstacle. And then we would do a backwards pass to update the belief of each object using this learned model. The model we had used 3 items. The current object is what gets updated, and then local information around it. So the previous and the next object. So it'd update that block, and then we go through and update the next one. And that's how we were able to scale this model to represent transitions for 9 blocks, 7 blocks. Well, 9, I think, was the most we hit because we've reached the boundaries of the U-shaped domain. So using this work, we were able to produce these types of conformant plans. And here is the example of execution of the robot doing an L-shaped arrangement. One thing I want to show you here is that we got interpretability for free. On the left, we have a representation of the object belief state, and we're just projecting it onto the video. We can see how the robots, how we predict the objects will be located during the actions, where we think the effects of them will be. And that is something that, these days is actually really cool about this work. Although at the time, I just made it to try to debug what I was doing. So in terms of the highlights of this work, I think what really is different about it was, the forward search and belief space and leveraging that insight from the vibratory ball feeders, where I, because of those things, it really directed the approach, that compact representation, the expansion, the compositionality. And then nowadays, I'm not actually working on this project. I'm working on other things. But I've realized that on, my approach to robots in other areas and other unstructured domains, often we don't just want to say, hey, robot, go do this thing. We also want it to do it in a certain way, a way that makes us comfortable around it, a way that we can understand and interpret what they're doing. And that was an aspect of this work that was just produced because I really pulled in, I would say, the solution space into the action space. So if you're interested in learning more, I have a whole thesis about it, and I'm happy to answer questions.
Awesome. Thanks so much. I actually had a question. So if I understand correctly, you represent the uncertainty as these intervals, but when we saw like the paddle, when it was moved up, it can sort of like either hit the block or not. There's like these 2 distinct modes. So in that case, does your interval have to span across both modes, or can you somehow like have disjoint intervals or something?
I think a quality of a research problem is when it creates more problems. There's directions for growth. one of the places I thought about growing into was having a bimodal or multimodal representation of the object's belief, or where things could be located, and then having a planner that would, approach those different, like, okay, if this happened or this happened. And in lots of work in conformant planning, they will handle that type of, bifurcations. In this work, we didn't. And I think it's something that is kind of interesting, because with a really simple, overly simplified representation, we were still able to solve these type of problems. So we actually got a lot out of it, which is kind of unique, like, wow, I can't believe we got that much out of it. But it also left a lot of room for growth in terms of where we could consider future work of a more flexible type of belief state representation, and a planner that would then, leverage these sort of separated structures. On the other hand, there was something kind of interesting about it too, where it acted almost as a heuristic, where whenever you would push things and they'd separate like that, and we couldn't continue exploring them because they no longer followed the structure, it would prune the search. So in some of the comparisons I did, I had like a particle approach where there was just like sets of states, and those would go slower, not just because of the difficulty to expand that representation, but because it would like have the search go into areas that might not be this structure was a heuristic in a sense, because it really pruned where you could go, because if the representation was so large, you couldn't continue expanding states from it. So I think the answer is, I considered it. I think it's a really exciting area, a direction you could go for this work.
And maybe a follow-up, like presumably if you had sensing, you could use it here. You're not necessarily like excluding the use of sensing. It's
right, like right here, I think one of the ideas I had, like this seems like it would really flow through execution monitoring, where you could continue doing the plan if unless you observe the object is outside of the predicted region. I think there was also, I think the thing I wish I had done, which was proprioception, where I'd look at where the robot's end effector was and use that to infer based off the geometry of the objects, whether or not this could have been a valid belief state. I think that's probably where I would have gone next versus the bimodal sort of representation. And again, that just means it was a cool research problem because it just had so many more options. But it didn't solve Tetris. So I actually jumped to a different type of style to solve those type of problems.
You need to have the blocks like sliding down or something. And yeah, anyway.
Yeah, that's, the sliding down is an interesting aspect of the thing the conveyor, but like the vibratory bowl feeders use, is that they don't just have gravity acting on them, like they have, and I wasn't able to fully gain all the insight there. But it's a really, really neat space.
That's great. Yeah, very interesting and very unique inspiration from those vibratory systems. Okay, so I guess we should move on though. Thank you so much, Ari. And you're sticking around to chair later. And next up is Angel. Angel is an assistant professor in CS at SFU. Her research focuses on the intersection of natural language understanding, computer graphics, and AI. She's also Canadian CFAR AI chair, and a lot of the work that she does in her group is focused on 3D scenes and 3D scene understanding. She got her PhD in computer science from Stanford under the supervision of Chris Manning. And she's also the recipient of the TUM IAS Pence Fisher Fellowship, which sounds quite impressive. So without further ado, I'll kick it over to Angel, who's going to talk about towards agents that can interact with 3D environments.
Thank you for the nice introduction, and thank you for inviting me to this robotics and vision conference. So I, just to give a bit more background about myself. So I actually did my PhD in natural language processing. And when I started out my PhD, I was doing mostly traditional NLP tasks that, well, involved text and text only. At some point for my thesis, I guess I started to hang out with graphics friends who do 3D. And I thought it was really cool if I could build a system that would go from text to 3D scenes. So the idea here is that you would have as input just a simple sentence like there is a living room with a red couch and a TV, and you would then be able to generate this whole room with a lot of different objects, you know, not just the mentioned object, the couch, which it has to be red, and the TV, but would actually automatically figure out where things would go and everything like this. And when I was working on this problem, I did come to the realization that language is underspecified. Like there's a lot of details about the world that we don't talk about. We don't talk about, you know, the couch should be placed on the foot, you know, it's not like oriented upside down, and it's placed on the floor. And in addition, the TV is usually placed with the front of the TV facing the couch. So in order to know of this, you actually have to have a lot of common sense, a lot of implicit knowledge acquired on where objects go. And so I'm not going to talk about this work in this talk, and I'm going to focus more on later talks that have to do more with vision and robotics. But this is where I started to understand, hey, there is a lot that you can learn from the world, from the 3D world specifically, that will help you actually understand language. And maybe if we want to develop an intelligent agent that can understand language, we need to start by understanding the world. And that led to me developing a lot of, working with different collaborators from different institutions at Stanford to create a lot of 3D data sets that basically allowed people to build models that would basically have this kind of knowledge of where you would say, you know, chairs would go around tables, what would that mean? And it would also enable people to use deep learning techniques, which are very data hungry on these 3D data, to do, say, shape generation or 3D object detection in 3D scenes. So this is where I started to get into 3D. But again, I come from a language background. So the question is, of course, you know, okay, there's a lot we can learn about 3D, but what can we do with language in 3D scenes? And if we want to build a robot assistant, a home robot that can help us around the house doing household tasks, maybe we want to ask the robot to, hey, bring me my coffee cup. This is a very, very simple example, but even here, in order to do this, the robot need to be able to have a lot of skills. I have a dummy robot because my work is kind of I would say the opposite of Ari's work, where the focus is less on the robot part, but on the other parts. And so this little robot or agent first need to understand, you know, when you say coffee cup, what object does that refer to? And then they need to be able to localize that coffee cup in the scene. So one of my recent projects, this is in collaboration with Matthias Nissner and Dave Ten-Atum, is to basically formalize this problem where we would basically take a 3D point cloud or 3D representation of environment and a description of an object in that environment, say a black chair in the corner, it is next to a table, and identify which object that's being referred to. So this is not really a new problem. This is a problem that people have looked at, people who do language and vision have looked at. They've typically looked at it in 2D. And I would say there are some advantages in being able to do this in 3D, in the sense that with 3D, you have information from multiple views that you can integrate together. In addition, you may have these long-range spatial relations that you may want to resolve, such as the chair that's furthest from the door. From a single view, that may be tricky, but if you had a 3D representation of the scene, it may be something that's possible. In addition, if you have a good scan, you would be able to get the real world sizes and extent of the objects. So there's just a lot more information in 3D. At the same time, there are actually quite a bit of challenge in working with 3D. One is that a lot of the spatial expressions that we use, they do tend to be what's called egocentric or viewer-centric. So it is from a specific point of view. So you do want to consider, what point of view the person is using. In addition, 3D technology or reconstruction technology is not quite there yet. So a lot of the representations or the data we're working with may be very poor quality, where the small objects are just a blob, and even you can see like there's a lot of missing surfaces, so the chair is not complete and so forth. But what I do believe is that if we have this data, then what it allows for is for investigation of different representations and models for both 2D and 3D. And this talk, I'm not gonna go into the detail of our model. It's a deep learning model. It uses some recurrent neural network to encode the language. It uses some 3D object detector to figure out where objects are and tries to match them. The main thing I want to just say here is that this is still far from perfect. We have a benchmark if people are interested in this problem, and you can see the numbers, or this is how accurate the system is at identifying the object position. And the scores, the main thing is the scores are pretty low. Newer methods use like transformers and better 3D object detectors, but there's a long way to go. But the thing is, that's one of the first steps in having a robot that can understand language and help us around the house. And now let's say that this little robot has now understood where the coffee cup is, but now he needs to actually go to the coffee cup. He can't just stand there and say, okay, that's the coffee cup. I've identified for you. He actually needs to go and move to the coffee cup. And so the next question is, what actions does this agent need to take in order to do this? And so recently, I think there's this term that's going around, embodied AI, where people do, when they study how to train your agent to learn to perceive, act, and I add communicate with physical embodiment. And this is kind of like robotics, except maybe we're less interested in the tricky part of the robotics, like the noise and the mechanics, and we're more interested in how does it just learn to do this. But it is very, I would say it's just a different view, and it's very closely related. And so typically here we have an environment. The agent can take actions and they can observe. And in order to do this, most of the work has focused on, they typically use reinforcement learning to train agents to act, and you can navigate. One popular formulation is this visual navigation, where you can navigate to an object either by name or following instructions. And you can do this in different ways, either just reactively, or you can build some memory representation or build map representation. I'm going to talk briefly about where do these observations come from. So I've kind of talked about, okay, we want to study this. We want to have a robot be able to learn to do things in our environment. But in order to do so, they must be able to move around and be able to have observations that train the agent. And in order to get these observations, what you need is you need two things. You need data and you need a simulation engine. And so this is something that I've worked on with, again, lots of collaborators, data from past data set efforts of 3D reconstructions. And the simulation, in some ways, you can think of it, it's very simple. You have an agent, you want to simulate the agent. So all you do is you just put a camera or virtual camera or render on it, and then you have some actions that allow them to do things. And then you add a Python interface, and that's your simulation engine. And with this, what you can do is you can then start to say, okay, there are all these different tasks that we're interested in. We are interested in, even for navigation, even just for navigation, you can say, okay, what can we do? We can decide that, okay, we want to specify where the agent want to go. How do we specify it? We can specify it as a point. A point, would it be a point in your coordinate space that's previously given, or maybe at each time step, I tell the agent, this is how far you're from the goal, and this is an angle to the goal. Or you can tell the agent, the name of the object, go to the chair, or go to a table. That's a bit more, I would say, less precise, has a bit of semantics, challenging in different ways. You can also give it an image that shows, okay, maybe this is an image of the chair you want to go to find it. Or you could say, okay, I want you to go to the chair in the bedroom. So that's using language. And there's all these different variations that you can explore. And my main point here is that, and I guess here is maybe also a bit of the nature of my work. I kind of work, I feel, in the outer loop, where I try to define data sets, infrastructure for other researchers that enable other researchers to do the work they want to do, and also define tasks that may be of interest to the community. But the idea here is that with these tools, with this infrastructure, then you can have these systematic investigation of, what sensory input is good. Do I need sensory input? If I have neural network models, what architecture is good? Do I need memory? How should I train my agent? All these different questions you can investigate. And okay, I'm gonna go back to my little robot. So now let's say that the robot has now learned to move to the coffee cup. I didn't go into any of the methods that actually do it, but let's just assume that happened. So now the next thing the robot needs to do is to be able to actually pick up the coffee cup. So far, like the simulation environment I've talked about is static, completely static. So we need to now go beyond being able to navigate in the static environments to interactive environments. And this basically requires a bit more than having just a render and some static assets. You need to have two things. One is you need to have physics engine, and you need to have also assets that allow interaction, things that allow you to cabinets that allow opening and closing. And this is, again, big efforts. So one project I worked on, this is in collaboration with UC San Diego, is we built this simulation framework called Sapien, where the idea is that it's basically just taking a physics-based simulation, and you basically, again, add Python interface, so it's easy to work with. So that's another key, I think. In order for a lot of this work to happen, you have to have interfaces that are easy for people to use. And the traditional robotics, I think researchers have focused a lot on the robots themselves, robots and maybe specific setups and scenarios. So you'll see that, there's many different articulated models of robots, which may be very accurate. And the environments that they work with, I would say, tend to be a little bit impoverished in the sense that it's mostly a block world environment. You can do a lot with block worlds. I think there's a lot of interesting things to do. But we're also interested in, if we want to talk about household robots, real objects that are what we would see. And so as part of the Sapien project, one thing we did is we created that data set of articulated objects where we had just connected a bunch of part objects So a prior project, the parts were labeled, and this project, made them movable. And so then this allows you to have this large scale set of objects that you can interact with. And so now you can start to investigate, generalization of your methods, learn methods from for seen object to unseen objects and so forth. And so for the Sapien project, one thing we did is we looked at door and drawer opening. So just door and drawer opening, and you can start to investigate the performance of different methods on this task. But this is still fairly limited in that the objects were not arranged in scenes, and that the task setup is pretty simple in the sense that, okay, you have a single object and you're just trying to open the door or the drawer. I'm not going to go into the results. Instead, I'm going to talk about this more recent effort called Habitat 2.0, again, with a whole bunch of collaborators mostly from Facebook AI Research and Georgia Tech. And idea here is that we really want to have interactive environments where you have, a whole apartment that the robot can navigate through and interact with different objects. And so the key to Habitat 2.0 is that it's 2.0 because there's an earlier version that I was not that involved with, Habitat 1.0. Habitat 2.0 is engineered for speed, and this is I'm not going to go into the engineering details either, but there's an optimization of assets and localized physics and rendering and clever interleaving of them. And the key here is that what we want to do is that we really just want to build a fast simulator that can go at many times real time. And we're also not the only, so there's a lot of people who work on robotics and this embodied AI as well. And a lot of them have recognized the need to build simulators and to basically have specialized assets for them to use. And so this is something that, a lot of different groups are doing. But the key to Habitat is really it's just much faster than the other environment simulators. And so this is showing that it can go up to 1,400 steps per second on a single thread with a single GPU. And if you have multiple threads and multiple processes and multiple GPUs, it can be much faster. And here's kind of my last point is why does speed matter? So in Habitat 1.0, when they were focused on visual navigation, or more specifically point goal navigation, one thing they learned is that the trend of SLAM, a traditional method, versus learned agent can change based on the amount of experience you provide to the agent. So if the agent for training these agents, if you don't provide it enough experience, you will think that, oh, maybe traditional SLAM-based method is better. We don't need to do any reinforcement learning. But if you can roll out and actually train these agents for millions and millions up to billions of steps, the trend reverses. So it is really important to have a fast simulation engine. But just having a fast simulation engine is not quite enough. You also want to design interesting tasks where the agent is going about and doing things. And one thing we're interested in looking at is these long range activities where it involves, opening drawers, opening fridges, picking up objects, placing them, as well as navigating together. And so this is pretty much the end of my talk. I would like to point out, some of the work I described really is just big, huge engineering effort with a lot of people. So I'm just play a very small role. And in addition, I think here's my main messages is that language and 3D is cool. Language provides a good way for people to interact with computers. And we also need to learn about the world to understand language. And for embodied AI, if we have data and simulation, then you can do systematic investigation of different tasks. And just lots of different tasks you can explore, and you should develop your own with either Sapien or Habitat 2.0 or any other of your favorite simulators. Okay, I probably went over time, but thank you very much.
Amazing. Yeah, we're a little over time, but maybe time for a quick question or two. I can start. So I think that the interactive part of this makes this a lot more compelling and interesting from a robotics standpoint. But it's still, the interactive aspect is still limited to articulation, if I understand correctly. Like it's fairly limited in the sense that the space of ways that you can interact with the environment is somewhat limited, or am I?
So you're I guess so I guess there's different ways to answer your question. One is fundamentally it is limited because we're relying on physics engines and physics simulators, and it's tricky to simulate, say, deformable objects such as claws and also rubber balls, pocket, and water, and those things are tricky. But I think it's I think what we need to do as a community is not to say that it's tricky, but to encourage people in graphics, who work on simulation, to build these simulators and to actually integrate them together in a way that's easy for robotics people, or people who want to maybe not work too much on robotics, but just the embodied part, to make it easy for everybody to use. So
Yeah, I think that makes sense. So what's Habitat 3.0?
Maybe it will have deformable objects. Yeah.
Sounds reasonable.
Yeah, don't know yet, but I really do believe, you should just tell the people what you want and get them to do it.
Great. Okay, so yeah, we're a little over time, so maybe we'll thank Angel again. And then I will kick it over to Ari to introduce the oral presentations.